Hey everyone, in this video I'll be covering the binary challenges as part of JerseyCTF. These are actually reversing challenges, not so much binary exploitation, but they're still fun. During the walkthroughs I'm going to go pretty fast. I'm pretty much just going to cover like this is how you get the flag. If anyone has any questions, feel free to reach out either in the comments or Discord, Twitter, email, anything. I'm always happy to chat. And with that, let's get started. The first challenge is plain, and we're just given one download file. For this challenge, all we had to do was run strings on it, so we'll do strings plain, and then let's grep and look for the flag format, JerseyCTF, and there's the flag. The next challenge is tracer. We're given a single download file. For this challenge, I looked at Ghidra, and so we can see within the main function, it's going to be looping over some stuff, and it's going to decode this flag variable. And it's going to use the S box and key and do some, XORing math or something. And after the flag has been decoded, it's going to compare our input against the word flag, and if they match, it says correct. Cool, so we could try to reverse this and go character by character or something and try to figure out what the flag is, or we could just load it into GDB and print out the flag, and that's what I did. So I'm in a Ubuntu Docker container. If you want to know how to do this, there's another video on my channel where I talk about getting this set up. But anyways, so I'm going to do GDB tracer. I'm going to break on the main function, then I'm going to run it, and then I'm just going to jump to the very end of the main function. And to do that, you just use the finish command. So now the main function has finished. And so if we go back here, we just said return 0. Flag should already be decoded at this point. So I'm going to say examine the string at the address of flag. And here's the flag down here, JerseyCTF. I'm never using libc again. The next challenge is my favorite game. We're given a netcat port. So if we connect to the netcat port, it was netcat. It says, I'm not familiar with the city, blah, 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 and we're supposed to give left, right, up, or down. So this looks like a maze puzzle. I'm not really sure why it was in the binary section, but it is what it is. So for the first one, I already know what the answer is, but I'm going to type up, and we get to keep going. And so if I type in the wrong one, it cancels or it says, that's not incorrect or something. So we don't know how long the solution is going to be, so we can just write a quick brute force script in Python, which is what I did. So this is my Python solution. Let me zoom in a little bit. Basically, we're just going to save what we know to be the correct path, and we're just going to brute force the next possible direction until we get something correct. So I have the path. This is the path we're going to take, and every time we get a correct one, we're just going to add to the path. And so this guess next function, all it does is it tries to guess what the next one is out of the 4 possible options, either left, right, up, or down. So I create a new connection. I send in the path I currently know is correct. And then I send in my guess, I sleep for a second, then I receive some data. If I see the flag format in the response, I know I have the flag. If not, if this if should in data, so it says like, should we go left? That means I got it correct and it's asking for the next step. So I add that to the path and I return from the function. And then from there, I don't know how long the solution is going to be. So I just say, guess the next one, print out the current path and sleep for 2 seconds just so I can see what the path looks like. Make sure it's not doing anything weird. And eventually we should just get the flag. And so let's run Python 3. The solve file. So this is the response it's getting. Wait, wrong direction. Eventually we got that should we go left, right, or up. So we know the first one is up. Then the second one is up. And it just goes through. We get down. And then a down. As soon as I saw left, I already knew what the solution was. I know I play video games. So up, up, down, down, left, right, left, right. It's a famous cheat. And eventually we get back the flag, so just a little bit brute forcing. Cool. The next challenge is insecure seed. For this, we're given a encryption binary, just a L file, and also this binary file that has the encrypted flag. Ghidra wasn't working so well for this one. I think it's because it's 32-bit and I don't have the function signature database loaded for 32-bit binaries. So instead I use this tool called dogbolt. Basically it's a way to compare all the different decompilers for a binary just to see which one works the best. Amazing program. I'm surprised this hasn't been shut down. But until then, I'm going to keep using it whenever I can. So right now I'm using hexphrase, which is IDA. It's a little bit hard to see. I'm sorry about that. But I'm just going to go quickly over the function just to kind of see what we need to do, and then I'll go over to the solve script. But anyways, there's this function in the binary called encryption algorithm. And we already have this file called encrypted flag.txt. And so we know that it's probably going to take this flag, run this algorithm, and then we get the output file. So we just need to reverse this function. And so if we look at this function, it's going to open flag.txt. It's going to fseek to the end of the file. It's going to get the size of the file. This is just how you get the file size, nothing special. It's going to allocate a buffer of the size of the file. It's going to read it in. It's going to grab the current time. It's going to seed random with the current time. Then it's going to do this for loop. I'll come back to that in a second. What's strange then, and very useful for us, it's going to create a buffer larger than the flag by 4 bytes, and in that buffer, it's going to set the seed, which is what was seeded to use to seed random. So very useful. Then it's going to copy it over, and it's going to save it to encrypted flag.bin. Cool. So we have the seed to srand. That's good. And it also makes sense. I mean, the challenge was called insecure seed. So we know what the seed is. If we look at the actual encryption algorithm, so it's going to go 4 character in flag. It's going to grab the flag character. It's just a little bit weird because it doesn't know the types. It's going to save the flag equal to some random modded by 256 plus 1 XORed with the flag character. Cool. So if we didn't know what the random values were, this would be very difficult. But it is, since we know what the seed variable is, rand will always be the same for that seed. So we just need to make sure that we call srand with the correct seed, and then we can just reverse the process. So not too bad. I have a solve script. This is what it looked like. So I copied out what we just had in that dogbolt decompiler. So this is the encryption algorithm. We're also given that encrypted flag.bin file. So first things I do is I load libc. So this is how you can call libc functions from Python. If we remember, the random number generator in Python is not the same as the random number generator in C. So we need to make sure we use the C one. So basically within Python, you can just call libc functions using this, the cdll from C types. Super useful. But anyways, so we load that in. Then we load the encrypted flag binary file. We read everything. We're going to grab out the seed. We have to use pwn tools to unpack it. So then we have the seed value. Then I just print it out. Then the rest of the file is the ciphertext of the flag. We're going to seed libc's random number generator by calling srand on it. And then this is that encryption algorithm. So we're going to, for each of the characters, XOR with libc.rand, add 1, modded by 256, and then print it out. And if everything works correctly, so I'm in a Ubuntu VM, or sorry, Ubuntu Docker container, we just do Python 3, solve, and there's the flag. So, fun challenge. The next challenge is sigcap. We're given a executable. It says it creates a string, figure out how, and it says reading the decompiled code might not be the best, time to read some assembly. So I loaded it into Ghidra here. When I saw this originally, I made it more complex than it needed to be. While making this video, I just realized a way simpler way to solve it. So I'll cover the way I actually solved it, and then I'll talk about the dumb, simple solution, which also explains how this had so many solves. I thought it was a slightly difficult challenge, but I realized I'm just being dumb. Anyways, this is the decompiled code in Ghidra. It's 32-bit, and I don't have the function signatures loaded into Ghidra. I need to do it, but I just haven't. So this is the main function. What's happening here is this is the signal function. And so it's setting up registering a handler for signal 4. So this is invalid instruction. So anytime this program sees like invalid assembly, this function will now be called. And it's doing some weird stuff. Like I said, the disassembly just didn't work that well for any of the decompilers. But we can see there's like some long array and different character offsets, and I just kind of guessed that somehow when this function is being called, it's going to access, this string by some index, and it'll create our flag character by character. And so we know the flag is going to start with a J, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if this function is somehow called with a 9, it's a J, we're probably in the right track. And so that's just kind of the path I went down. There's all these different functions here, and what they're doing is they're going to be calling some invalid instruction. So there's like this UD2 and then this invalid assembly. So this is going to trip that signal handler. And we can see this is the first one. It's going to push 9 onto the stack. And then it's going to do some stuff. And then it's going to call that invalid instruction handler. And so here's our 9, which corresponds to J. And if we go back to the next one, we see it's pushing 2. So that is a B, C, so that's J, C. And if we go through, we'll see it's JCTF and then the rest of the flag. And so again, this is the dumb way to do things, but I just went through function by function. I looked at all these push statements, so the next one is 13. And I have a piece of paper, I wrote them down, and then I copied it over to a Python script. So this is my solve script here. Like I said, I just copied them all down. Here's that mapping. And from there, I just looked them up character by character. So you can do Python 3 solve. And here was the whole flag. So, it took me like an hour to solve this one, when really it should have been much faster. So like I said, while doing this write-up just a minute ago, I realized there's a way simpler way to do this challenge. And the trick, I don't know if it's a trick, but this is a memset call, and it's memsetting this buffer right here. I just didn't really look at it because I didn't really know what it was doing, but slightly frustrating. So it's mem setting this buffer. And I realize now that it's actually writing the flag into memory. So all we had to do was just run this program, wait until right before it exits, and the flag should exist within memory at this offset. And we don't even have to calculate the offset. So what we can do instead is, I'm already in a Ubuntu Docker container. We're going to do GDB, it was sig something. Let's break on signal, and we're going to run. So right now, this is the main function, and this is the signal handler, which is this function right here. From here, we can just finish. It would be nice if we could finish main, but it's getting stuck on all these invalid instructions and then go into the signal handler. It's not a big deal. We could actually remove the signal handler within GDB, but I'm just going to hit continue. GDB is just being nice, and anytime that signal handler is called, it's breaking for us, which is nice. We can see program received, sig illegal instruction. But we can just skip forward a whole bunch of them. I mean, we could just keep going until the very end of the function. But what we can do now in Pwn debug, there's a really cool tool called search, which will search for anything within the running process space. We'll just search for JerseyCTF, and we can see, yeah, it's actually building out the flag for us. So we can just keep hitting continue a bunch of times. Let's see how far it is. Now it's all the way to here. What are we going to? It doesn't matter. Continue, continue, continue. Actually, let's just break here. Continue, continue, continue. So we'll wait until the stack frame is empty. So now that the stack frame is empty, we know we've finished everything. And so we're going to search for JerseyCTF, and there it is. Stack it, great, check it. So all we had to do was inspect process memory, but either way works. The next challenge is linear. I didn't solve this one during the CTF. The challenge came out a little bit late and I just didn't have time to finish it, but it wasn't too difficult of a challenge. So I'll be covering the reversing process, just giving an outline of the solution, and then someone else posted their solution in Discord, so I'll just quickly link to it. Props to that person, and we'll cover the solution. So it was called linear, which is already a big hint. And we're also given another hint. It says, can you make the program faster? And we're given one download executable. If you run the executable, nothing happens. It's just doing some calculation. So we need to reverse it. So I loaded it into Ghidra. This is the main function. So we can see it's going to be loading 2 buffers. Then it's going to be looping over. I'm doing L on the keyboard and then I, just to rename the loop index. So for I, setting some variable while I is less than this value. This value is huge. There's no way we'd be able to loop over this many times. So weird to see why the program was hanging. This is, I don't know, trillions. I mean, a back of the napkin calculation. So if your CPU runs at 3 gigahertz, let's say, that's 3 billion operations per second. You can on order do, maybe a couple 100 billion loops. Again, back of the napkin, rough estimation. There's no way you'd ever be able to do this big of a calculation. So that's where our issue is. Then it's going to call a function called matmul, and then it's just swapping these buffers. So this is, we can kind of guess from the name, it is matrix multiplication. It's pretty nasty when you first look at it, but we know what the inputs were. They were 2 long buffs, so we can do long star. So I did Shift L, or sorry, Apple L on a Mac to rename the types, or change the types. So now these are both long pointers, or an array of longs. And so we can see it's a little bit cleaner. There's also this mat buffer here, mat variable. It is also a long star. Technically, it's actually an array, and we should do that, but we would have to calculate the size, and at this point, we don't know what the size is. I'm also going to rename these variables to I and J, so this looks much cleaner. This is also, we can change this to 36 instead of hex, make it just a little bit cleaner. And from here, we can kind of see that it does look like a matrix multiplication algorithm. It's going to loop over for I and J. It's going to set, we'll call this one in and out. That's going to set the out I equals to 0. And then from here, it's just going to iterate like when you do, this is matrix multiplication with a column vector and a matrix. And so it's going to loop over one of those entries. I like to think of it sliding, but it's just matrix multiplication. And it's going to sum it out into out of I. So as a result, we're going to get a new column vector out of this. So that means mat, if this is iterating over 36, that must mean this mat variable is a 36 by 36 matrix. And so all we're really doing is we're taking that input vector and we're multiplying it by that big matrix, and we're going to do that operation like 16 trillion times. So the hint was that the problem was called linear. These are all linear operators, which also means that you can actually, instead of multiplying the column vector by matrix, 16 trillion times, you can actually just take that matrix and raise it to the power of 16 trillion or whatever. That still sounds impossible, like we're just moving the multiplication somewhere else. But there's an algorithm called like fast mod or whatever you want to call it. And so doing that, we can actually take the power of the matrix to 16 trillion. And that's what the solution is. There's one complication with the solution, and I'll talk about that in a second, but there's one complication. We can see it's doing these mod operators in here. So this is, it's modding it to 4 bytes, but there's the 7 FFF. I think this is the positive portion of a signed integer. I could be wrong, but I think that's what this is supposed to be. Not really sure why it's here. But it also means we can't just use default, matrix implementations found elsewhere, because this is kind of an unusual sort of thing. But yeah, so our solution is we're just going to re-implement this matrix multiplication. We're going to implement the mod pow algorithm, and then we also just need to make sure we do this modulus operator all the time. The mod pow algorithm, it's not too bad. If you're not used to thinking about binary, it might be a little bit confusing, but basically what we're going to do is, the idea is, so we can easily multiply 2 numbers together. But if we wanted to multiply the numbers together, 16 trillion times, that'd be impossible. But there is a little bit of a shortcut, and the shortcut is like we can multiply 1 by 1 by itself, or like one vector by another vector by itself, and when we're done we get 2 of them. But then we can just double that, so we can multiply 2 by 2, so then we have 4. So we have a vector that has 4 times itself, and then we can just keep doubling it like that. So we can do 4 times 4. Now we have 8, 16, 32, blah, blah, blah. And you can kind of climb up this like binary chain. From there, again, I think it's best just to kind of implement this algorithm yourself. Like it is a cool algorithm. Basically, we're going to take the result every time we do a doubling. If there's a 1 in that binary place, we're going to add it or multiply it to our result vector and save it. So on every step of this binary chain, we're going to do that doubling algorithm. And whenever there's a 1, we're going to multiply it with our like out vector. And when we're all done, we'll actually get the result of this, fast mod pow. So really the, time complexity is just, the log base 2 length of whatever we need to do, which is something we can do. If that didn't make sense, I apologize. But that's just, how to think about the algorithmic complexity of this algorithm. Anyways, like I said, the solution was posted in Discord, thanks to Cryptoverse. So I'm just going to cover their solution. Again, props to this person for actually solving it. Here's Cryptoverse. They saved the matrix to a text file. So that was that big matrix, 36 by 36. Then they saved the buffer. So this is the initial starting buffer. So there's that column vector, and we're going to multiply it by, 16 trillion matrices. They implemented 2 different matrix algorithms. So there's matmul. So this is, big matrix by big matrix. So this is going to multiply the 2 36s. Really, it's just doing a matrix squared because it's going to be the same matrices. Not that it matters, but we just multiply those 2 matrices together. This is matmul 2. So this is the matrix times the column vector. So this will be our final thing. And this is that fast power algorithm I was talking about. They do it recursively, which is interesting. So you can either do it recursively or you can iterate through bit by bit, and there's a couple different ways you can do that. Like in Python, you could take the bin string. So you take a value, you call bin on it, you slice off the 0 and the x at the very start, or the 0 and the b at the very start, and from there you just have a string of 0s and 1s. And so you can iterate, you have to do the reverse of that, but you can just iterate character by character. You can also just do a shift left by 2. You can take your integer that you're trying to iterate over. You can do a mod 2 to see what the very last bit is, and then you can shift left by 1, and so that'll divide it by 2, and you can see what the next bit is. They all work, but basically, like I said, if there's a 1 in there, they're going to return the array, so this is their exit condition because they're doing it recursively. Otherwise, if it's a 0, they're just going to do that squaring operator. And if it's not a 0, that means it's a 1. They need to add the result. But anyways, that's the fast power algorithm. From there, they're just going to take that matrix, the starting matrix, and they're going to bring it to the power of 16 trillion whatever. And then they're going to take out the result and print it out character by character. So pretty cool challenge. The next challenge is decryption-server. We're just given one download file. So if we load it into Ghidra, we can start taking a look. It's going to do some init server. So this is loading a real server somewhere. It's going to do socket listen down here. Whenever it accepts a new connection, it's going to spawn up a new thread. So we can take a look at that, some routine function. Skipping over most of this, we can see there's some command parser. And here looks like some interesting stuff. So it looks like if we pass the decrypt command, that's good. It's going to check to see if it's a valid key. and the valid key check is just it's doing a length check. So the key needs to be of a certain size. Eventually it'll call this decrypt routine. Cool. So it says thankfully this was not stripped, so we get all the variables, which is super nice. So we can see that the key our attempt is going to be converted somehow. Then it's going to generate a key using this keygen function, and it's going to check if it's the true key. And to do that, it's just going to do a raw byte comparison. So we know keygen ox deedbeef will generate the correct key. So that's great. We know what the correct key is. And from here, if we kind of scroll down, eventually it's going to do this decrypt flag, take our key. There's a little bit stuff going here, but basically it's just going to loop through, and it's going to be doing an XOR with the key and this buffer here. Cool. And then from there, it's just going to write it out. So we could try to run the program and generate the correct key and blah, 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 all that stuff. But we could also just be lazy and have GDB generate the key for us and then grab out these values and do the XOR ourselves. That way we don't have to worry about any of that stuff. And so that's what I did. So we can actually run this in GDB and have it call the keygen function for us. So let's jump into an Ubuntu box. Let's do GDB. It was called server. I'm going to break on main. Then I'm going to run. And then I'm going to print, it was keygen, I think? Keygen, ox, it was deedbeef, which got me mixed up at first. So cool, GDB just called the function keygen with deedbeef, and this was the result. So then we can examine, let's say 20 unsigned bytes at this address, and this is the correct key. So now we can copy that out and put it into a solve script, and I put it right here. The next thing we do is it's going to XOR that key with the correct solution here. So we can just copy this value out. To do that, you just highlight some of it. Oh, it's being weird, but you can highlight all of it, and then there should be a option. Oops, where'd it go? You can then do special copy, copy special, and there is Python. You can do Python list or byte stream, whatever you want. And you paste that into the solve script. And then at that point, all you have to do is XOR. So to XOR, I do import pwn.xor. This tool is amazing. The pwn XOR, simple, but all this works. It's going to do the repeating stuff for us, and this should just print the flag for us. So let's exit out here, clear, Python 3, solve. Congratulations on decrypting the flag. Here is short, blah, blah, blah. JerseyCTF reversing is fun, do more. So fun little challenge. The last challenge was Infiltration. We're given 3 different files. The idea behind this challenge was there's this like custom language, which eventually we figure out what this custom language is, and they have some disassembler in this custom like stack-based language. So they give us the current process memory, the currently executing function block, and a description of the opcodes. And what was also very important is if you click on this person, they have a bunch of repos related to this. Let's take a look at the files real quick. So this is the decompiled function, I guess, and it's written in this kind of strange language. I think the language is called Rage, which you find out by just doing some Googling. But it's like the stack-based language. We can see like it's doing pushes and subs. There's a function called decrypt here, a function called print, main. You saw some XORs, some set function, loading in like, big numbers. So we have that. We also have that memory dump file. So, we can take a look. Let's go hex dump memory. I played with it for a little bit. It's not really obvious what this is supposed to be, but we have a big chunk of memory, I'm guessing process space. And the last thing was this opcodes.md. So this is the description of that stack-based language. And so really the challenge was either you need to find an emulator or you need to implement this language so that you can call that decrypt function and decrypt the flag. Unsurprisingly, only one person solved it, and thankfully they did a write-up. They're very well known and they do great write-ups, so much appreciated. They actually have a blog and they do a lot of very technical write-ups. A lot of times whenever I'm doing a CTF, I'll Google around for hints or tips or something, and this blog pops up all the time. Especially for I did one with PHP filter chains a month ago or so, and they had just a great article. So definitely check out this blog. But anyways, this is their solution. I'll put a link in the description. Highly recommend checking it out. But pretty much kind of like what we said, they implemented it in Python. So there was that decrypt function. Again, check out the article itself. But they implement the decrypt algorithm within Python, and they dump everything out. And then they split it. They did 2 different Python things. This is the next set of functions for actually like doing some like XORing math with these like static values. and you can kind of see like these are these instructions. This is what it looks like in Python. These are these instructions. They do it here. And at the very end, after doing all that stuff, you'll get out the flag. So props. They were the only person that solved it. Definitely a little bit of work. I was nervous that it was going to be a rabbit hole that I would, spend a lot of time on and never solved. So I didn't even really try it. But thankfully there are people way braver than me. So it's very cool. Anyways, that is all the challenges. If anyone wants a write-up of another challenge, please just let me know. Happy to do it. The binary section was by request from 2 other people. And with that, I will see you at the next CTF. Cheers.